Okay, let's start. Do you have any questions? Okay. So maybe let's start by stating a error. Hold on. In 6.9 solution, I believe, from last time. So the problem 6.9 states this: fxy is 6/7 x squared plus xy/2, x between 0 and 1, y between 0 and 2. Okay. And I think a question like question C asks you to find probability x bigger than y. And so while it's pretty straightforward as in what you should do here, what you expected to do. So what happens is the following. First of all, the region, right? The support of the random variable is like this, right? So the line x equals to y is this line. So the region, right? X bigger than y is this one right here. So it would just be the double integral, right? Of x equals from y to 1 and y from 0 to 1, right? Of the joint PDF. All right. So the mistake last time, I mean, if I recall correctly, I think this is what I did. Is that I drew the region like that, right? And it's pretty, I don't want to call it a standard mistake, but I didn't draw it to scale. And so I believe when I draw the line x equals to y, right, it results in this region or this shape. The reason why is because I think I remember if I asked if we should do this dx, dy, dy, dx. Okay? And the point is that this is incorrect, right? As a region, because, wow, the actual shape is this. And you see that the mistake came from the fact that the region was not drawn up to scale, right? I would say that, well, of course, there's no excuse for the mistake if we did and make the mistake. On the other hand, it just shows that, right, in this, let's call it calculus 3 problem, we definitely want to be careful, right, with, let's say, our visual, right, our sketch and things like that, because things that probably usually won't have a consequence, like drawing things up to scale, will have a consequence if we are not careful when we do integration. So I just want to kind of point that out, that probably, right, I wrote down the wrong thing for this. Any question? Sorry, give me a moment. I'll be right back. All right, sorry about that. Let's continue. Okay, so yeah, so let's continue. So yeah, that was the mistake from last time I want to point out. Now, okay, so let's move on to 6.2, which is the topic of independence. Let me see, that's the case. Yeah, independent random variables. Okay. And here it's pretty straightforward actually, but there are quite a few things to say about this. First is that this is basically kind of like the idea of the random events, right? So recall, right, that two events E and F are independent if, right, probability of E F is probability of E times probability of F. And you can also, right, have the conditional version when basically, right, conditioning has no effect on probabilities. So with random variables, I think is much more easily defined using the product version rather than conditioning version. Because you have to be careful like this, right? Let's say two discrete random variables. So the discrete version is following. XY, right? Let's say XY are discrete. Then X and Y are independent if probability X equals to I, Y equals to J is equal to a product. And the key is for all ij. That's the key. Basically, I would say this is not surprising, right, to anyone that that's sort of what happens, but it has to be true for all ij. And what's the theme here? If you look carefully at this is the joint, right? The joint mass distribution function. And then these are the marginals. Right? So the idea is the joint is the product of the marginals. When you have that, that is independence at the level of random variables. Okay. And similarly, right? And the reason why is because if you remember that, then for the continuous case, it's the same thing. If you have two continuous random variables, so they have joint density, then x, y are continuous. X, y are independent if the joint density is the product of the marginals for all, right? I mean, when we say this, when we say the joint density is the product of the marginals, of course, we mean at the level of the functions. So that means kind of automatically true is true for x, y. But that's the case. Okay, any questions so far? And finally, right, so I mentioned, right, that random variables doesn't have to be discrete or continuous. They can be neither, right, neither continuous nor discrete. So if that's the case, then the general results are following. X and Y are continuous. Sorry, X and Y are independent if the joint CDF is a product of the individual CDF or the marginal CDF for all X, Y. So if you remember, right, the joint CDF just means jointly X, Y less than equal to these values. And the marginal is the marginal CDF is like that. All right. So basically what it means, right, is that, I mean, so is if you have either one of these being true, then that will imply this is true. But if we don't have, right, random variables that are discrete or continuous, then we can use this version. Of course, in this class, you guys will 99.9% of the time be dealing with this. But yeah, I'm just going to state the general case just in case. Any question? All right. So notice, right, it also works in the reverse direction because of course this equality, right, can go in either way. What does that mean? We tend to think, right, that this is used to tell us when two random variables are independent, and you're correct. That's one way to use it. But another angle, right, is the following. If you know random variables are independent and you know their marginals, then you also know the joint, right? Because the joint will be the product of the marginals. So if you know random variables are independent and you know the marginals, then you also know the joint. Does that make sense? So let's say indirectly. Is that okay? So let's see how this works. How this works is, for example, let's look at question 6.10. You have e to minus x plus y. Okay, so here I'll tell you what the question is. Question A says find probability x less than y. Question B says find probability of x less than a for some number a. And so probably the taste of this is section 6.1 rather than 6.2, right? Because it's just about the joint and finding some probabilities. But, right, you should get into the habit of investigating the margin, the joint or whatever you're given, right? And look at the structure, even if it's not directly, right, given to you. For example, if you look at this density, what jumps to your attention? What is special about this joint density? Answer. This is e to the minus x times e to the minus y. Therefore, here x, y are IID exponential 1. So IID, remember, right, stands for independent, identically distributed random variables, right? Identically distributed is because they're both exponential 1. That's not super important. I mean, it is, but it's implied by exponential 1s, right? The independent part is much more important. They're independent. So do you see why that's kind of sort of, it will help if you recognize that fact, because what would this be here? So first of all, right, let's see how this is done in the good old-fashioned way, meaning using the joint. If you use a joint distribution, then what is p of x less than y? Well, it would be what? The integral e to minus x plus y, right? dx dy, x less than y, so integrate from 0 to y is from 0 to infinity. Here, I may or may not need to draw a picture because it's 0 to infinity. But if you want to draw the picture, right? And you should, you're encouraged to. It's just, if only to get into the habit, right, of visualizing things, then, right, the region of support is everything, right? On the first quadrant. And so x less than y is this region. So x goes into y, y goes into y. Okay. And what would this be? Well, you integrate dx, right? So y is a constant. So it's e to minus y, and the other one is 1 minus e to minus y, right? And now you look at this one. This is, of course, 1 because it's the entire density of an exponential. The second one is e to minus 2y. Well, it's almost like a exponential density, right? You miss a 2, so you put a 2 there, put a 1/2 there. So that's minus 1/2. So the answer is 1/2. I mean, I'm doing it quick because, you know, the integral is straightforward. You could just kind of take the integration and then plug in and you should get the same answer. Any questions about this? So the point though is that this is done by joint density, right? The good old fashioned way. You know, you just plug in and you do the integration. However, if you observe that the random variables are IID, here's an alternative solution. The alternative solution is to observe that p x less than y is equal to p of y less than x. Two reasons. The first thing is because x, y are exchangeable, and this is a new concept, but basically it means that you can swap the role of y and x in the joint distribution and it's the same distribution. What's the reason? Because they're IID, independent identically distributed. So, right, the joint is a product. So it doesn't matter if you multiply one first or the other first. Or if you want to make it even a little bit more simple, x and y are symmetric here, right? One is the behavior of them are similar, but you need that independent to make it work. So that's the first one. The second one is a little bit more subtle, but they're continuous. The reason is because if you don't, you might have equality on one of those and it can get tricky. But either way, right? If you kind of work through this real quick, you'll see this. On the other hand, this will be 1 because, right, there's no equality. So either x less than y or y less than x, so together is 1, meaning it's 1/2 each. In fact, right, this doesn't require anything about exponentials. As long as you have IID random variables and continuous, automatically it's true that p of x less than y is 1/2 by this argument. Right. Having said that, do you need to do it this way? Absolutely not. This is as valid as anything else. But recognizing this pattern or this concept, let's say it's a deeper way of doing things, is simpler, but it's more sophisticated and it's more general, right? You realize, as I said, this result is more general than just exponential. So you realize that that's not important anyway. You just need IID, continuous random variables. But the independent part, right, plays a big role. And if you don't observe that, then you just do it, like I said, the good old-fashioned way. Any question? Like I said, which is fine at this level, right? I have nothing against that. For math, 4, 77. you're okay doing it whichever way you want. But sort of like looking into the future when you do more advanced works, then if you don't catch a pattern quickly and be able to generalize better, then it's just harder for you to do more complex problems. All right, so let's take a look at B, right? Probability x less than A. Well, what's the good old-fashioned way of doing it? The good old-fashioned way is, of course, just to calculate out income, which of course, right, will be e to minus y, 1 minus e to minus a dy. And this first integral is 1. The second integral is also 1 with that constant, so it's 1 minus e to minus a. Pretty simple. On the other hand, this is even more quick when you recognize that x is an exponential 1 from here, right? Because these are products of two individual marginals. Therefore, probability x less than a is directly this from the knowledge of the CDF of an exponential 1. So what I'm trying to say is the double integral calculation is some kind of repeated work that we can skip if we recognize something going on. Any question? All right. So let's do a second question. Second question has to do with telling you how to recognize independent random variables, or to be careful with some cases. Let's see. Now, if you recall, we looked at a uniform on a circle, right? Before, meaning that something like this, right? So the joint is 1 over r squared, pi r squared, right? For x squared plus y squared less than equal to r squared, and 0 otherwise. Okay. Is xy independent, or are xy independent? Explain. What do you think? Are they independent? Well, this is a constant, right? So constant seems to be independent of x and y. So it seems like they're independent. Well, here's kind of the kicker, or here's what I want you to compare with. More often, you will have this case, x, y, uniformly distributed on a rectangle, meaning this. So one of them is A, one of them is B, like that. Okay. So the joint is 1 over A times B for 0 less than equal to X less equal to A, like that. Same question. Are they independent? Explain. Any difference? Circle, rectangle, who cares? All independent, right? The answer is yes here and no here. Okay. And maybe that's a subtlety. I don't know. To me, that's kind of interesting. At least on the first time you see it. They're both uniforms, right? Meaning that density is constant over the support. But one is independent, one is not. Why not? Why not here is because the shape of the region is also super important. Actually, the shape of the region, the shape of the support also is part of what the joint density looks like. Here, the shape of the support, you see, X and Y don't influence each other. No matter where X is, Y is between 0 and B. No matter where Y is, X is between 0 and A. On the other hand, if you remember, right, here, because of this, if X is over here, then Y is only from here to here. If X is over here, Y is from here to here, right? So in some sense, the smaller X is in terms of magnitude, the bigger Y can be in terms of magnitude, and vice versa. That alone tells you they're not independent. Okay, so far. So those are intuitive arguments to help you think along the way. What's the rigorous proof? Rigorous proof is here you have nothing better to do than to derive, to calculate the marginals, and to check whether the marginals product, the product of the marginals is the joint. Okay, so let's see. Let's start with this because it's easier. The marginal here is what? Integrate out the y, right? But y goes from where to where? As we explained, right? For any value of x, y goes from 0 to b. Therefore, this is 1 over a. Similarly, which is and so you see, right? The the support is also very important. we won't go beyond this here in this class, but in 481 in statistics, if you ever take that course, then the boundary, right, the support will be part of the density as written in using an indicator function. All right. And so in that sense, you see that the product of the densities will also have the indicator function attached with it. Okay. But like that. So that's why they're independent. Any question? Now notice, right, what's more? What's more is jointly uniform on a rectangle means that individually, marginally, each of them is also a uniform from 0 to A and 0 to B. Okay, they're uniform. So marginals are uniform. Here's a question. We do know that the distribution of X depends on Y, etc. right from here. But even for a fixed X, let's say, is Y uniform from here to here? Is that true? Or for a fixed Y, is X uniform from here to here? In other words, if you have a joint uniform on a circle, are the marginals uniform? Well, let's see, right? Let me erase this. Okay. This is from, so for fixed X, right? Then Y goes from square root of minus square root of R squared minus X squared to R squared minus X squared, right? dy, which will be 2 square root of R squared minus X squared over pi R squared, right? Where X runs from minus R to R. So first, let's settle the question of independence by a same calculation, right? Because X and Y are symmetric here. So very directly, does this times this equal to that? The answer is no. So they're not independent, right? So that's very, very detailed and no intuitive argument is required, but no, right? And also you have to kind of pay attention to how, right, the boundary here, this indicator function multiply do not get you to this indicator function. Notice, right, this is kind of a rectangular kind of region. And this is true because when you look at the marginals, all you can say is they're between minus R and R, which can result in a square rather than a circle. But anyway, right? Second, is X uniformly distributed? The answer is no, because the density of X depends on X, right? It changes as X changes. So marginally, these are not uniform random variables to begin with, but jointly, they are uniform over a circle. That's the subtlety, right? So these things are so that you can contemplate, right, how things behave jointly and marginally. Because I would bet that our kind of intuition is that if things are jointly uniform, then marginally they're also uniform, which is entirely not true if the region is not rectangular. And also the question of independence. Any question? what else will be application of independence? Independence can be used in many ways. Let me see if the max and min is included in this calculation. Let's just show you anyway. So this is called the order statistics calculation. And we're just going to do the max and the min, okay? Which is, you see this more in, like I said, Math 481. But the question is like this. Suppose you have x1 up to xn, IID, right? Independent, identically distributed. Let's say they're all with densities, individual density, right? Let's call them that. So these are the marginal density, right, of each of the x's. Of course, 3, right? Find the PDF of y equals to the max. How do we proceed? So we proceed, right, as a theme of finding densities of something. We start with a PDF. Oh, sorry, we start with a CDF. Probably y less equal to y, right? What would this be? Well, you plug in the definition. Right. Then you analyze the expression. Well, the max is less than or equal to a number when what? The max is less than or equal to a number when individually all of them is less than or equal to that number, and vice versa. And of course, right, this is just a joint CDF. So it will be the product of the individual CDF. Right? And what do we know? We know that they're so we use the independent, right? But they're also identical in terms of their distribution, meaning that all of these are the same numbers. So therefore, we can just say that this is the CDF of the distribution raised to n power. Any question? Oh, you know what? Sorry. This is y, right? Not x. Y is this value. And x is sort of like the, the model, right, for the individual marginal. Now to find the PDF, then what do we do? We differentiate the CDF. Which means we differentiate this expression with respect to y. Well, what will we get when we do that? We will get using the chain rule. Right, that's the outside. The inside will be the density of x. Any question? So this is the classical calculation, right, of the max of independent, identically distributed random variables. You should think of what the minimum calculation looks like. But the hint is it's very similar, right? You just have to change the direction of the inequality correctly. Are you okay? Any question? All right. Now let's look at question 612, which is supposed to be, let's say, assigned last Friday, but it'll be assigned today, right? Because the topic is more along the line of 6.2 rather than 6.1. It says this: the number of people entering a drugstore is Poisson 10. Let's say per hour. Compute the conditional probability that at most 3 men entered the drugstore. What's just called the store, whatever that is, given that 10 women enter in that hour. What assumptions have you made? Okay. So there's a lot going on for this question. It contains many ingredients of many aspects of probabilities, even connected to something called compound random variables. But let's just do this slowly, right? So how do we start with this kind of question? Well, we start by modeling, right? Or we start with writing down the symbolic model for what we're given and what's being asked. So what's the relevant random variables here? They are X, right? Which is the number of men, and Y, which is the number of women, right? Entering the store in that hour. What do we know? What information is given and what's being asked?
Are they both like Poisson 5? Because you assume that it's equally likely a man or woman.
Good, but you're jumping to a conclusion here. You're not wrong. That will be the answer. But when you think about it, how do you know that they're Poisson 5?
Is it that's
True.
like equally likely that either would enter the store? So if it's like Poisson 10, you like
No, I get it. I mean, that's the danger. That's the danger here. So the result is correct. What you said is correct. But let's just pull back and say this, right? And yes, the assumption is that they are equally likely to be men or women, right? So each person, so the assumption, each person is equally likely, right, to be a man or a woman. And what's more, this should be independent of the other customer's gender, right? However, so notice the subtlety here is the following. Basically, you have so many customers, right? Let's say, I don't know, 6. And then let's say 2 of them are men and the other one are females, right? That's just one possibility, right? And among so many. So what's going on here at the heart of things is you have a discrete random variables, which gives you a random numbers, right? Random integers. And then among those, you have types. You can have type A, type B, type A, type B, type A, type B, right? With some probability. Here you say 50-50. But what's unclear, what I say, is the jumping in the conclusion part is why is it that when you look at the subtype, they still retain the original distribution of the overall numbers, right? Case in point, if you're so confident, let's say if that is true, then are you sure if the question or the answer remains the same if you change this to, let's say, instead of Poisson, you have a geometric random variable, or you have a hypergeometric, or you have a binomial, or you have a negative binomial. You understand what I'm trying to say? Say people entering the store according to a geometric random variable. That sounds pretty weird, but who knows? But if that's the case and every other information is the same, do you want to say that they're geometric individually as well, with something split into a half. You understand what I'm trying to say? So while the answer is true, we need to show the calculation leading to that conclusion rather than say, yeah, it must follow that way. Because then how do we point out that the argument won't work if we change it to some other distribution? Do you understand? So let's see, what do we have? What we have going on for us right now is only that x plus y is what? Is Poisson 10. That's all we have. What's being asked? What's being asked is probability x is less than or equal to 3, condition on y equals to 10. Right? Which is the same as asking probability of x less than or equal to 3, comma y equals to 10 divided by, right? And suppose that, and it's not the case here at all, but suppose that I even grant you that somehow you know that individually x and y are Poisson 5. What's still missing to answer this question? What's still missing, and you'll see that the goal here is the joint distribution of xy. Right? That's the implicit question all along to answer this question. So in a way, this question jumps a bit far to this, which is fine, whatever. But probably it's better to work with the joint first before we even go there. Because that's exactly what's being asked. Well, what's needed. Okay. And let me tell you the target or the answer. But again, let me strongly warn you. The answer here is in no way obvious. Okay, I insist. They have to be supported by conclusions. Oh, sorry, by calculations. And what's the answer? The answer is x and y are independent. Okay, Poisson 5. And so, two ingredients here, Poisson and independent. Both of them need to be shown. Now, in case you think Poisson 5 is obvious, you think independent is obvious as well? And in case that you think is obvious from here, from this assumption, that's not true. The reason is because we say that individually, the gender of a person is independent of the gender of another person going to a store, which is kind of obvious. I mean, not obvious, but it's a very reasonable assumption. On the other hand, X talks about the total number of people of a certain gender coming to the store. So why would that, or how would that be independent, right, of the total number, right? Of course, this will lead to that for sure, but they are not the same statement to begin with. And that's why it's not obvious. Okay. So these are all the, let's say, subtle aspects of this problem. So what do we do? What we do is to start with the joint, which is, let's say, that. Let's just work with the abstract calculation. What's the probability that there are I women and J men coming to a store at any hour? How do we calculate this? The key is to drag in the sum somehow, right? Because that's a given information that we need to use. And so we will use it by doing conditioning. Right. And so let's see. It's pretty obvious that, right, the joint, I mean, this is really just from P of E F is P of E given F times PF, where we intend, right, for this to be F, and this and that together is EF. But if that's the case, then what do we fill in here? X plus Y is equal to I plus J, right? That's the only thing that can be possible when individually X is I and Y is J. Okay, so far? The reason is because we know what this is, right? What is this? This is Poisson 10. Or you know what? Let me do a general calculation here. Doesn't matter, right? Let's say it's Poisson lambda. X plus Y is Poisson lambda. And this will be e to minus lambda, lambda to the I plus J over I plus J factorial. Okay. What about this? Now here's something that will be obvious. If you know that the sum, right, the total number of people entering the store, let's say it's 13, let's say. And individually, each person has a success. I don't mean anything here, but let's say success probability of P to be a man, and the other probability of 1 minus P to be a woman. Okay. Then what are we talking about? We're talking about a binomial random variable, with this being the total number of trials. And this is the number of trials happening in one category, and this is the number of trials happening in the other category, which means this is I plus J choose I, P to the I, 1 minus P to the J. And again, I do recognize that this is a half each, right, in our assumption. But let's do this just to show you the general calculation. Any question? And this is the key calculation that I say is subtle to lead to the conclusion that that's the case. Right? Now, how do we simplify this? Well, first of all, right, this is I plus j factorial, I factorial, j factorial. And we will group the I power together. And the j power together. And what's more, e to minus lambda here will be split into e to minus lambda p, e to minus lambda 1 minus p. All right, like that. Why? Because now what I have is this expression is a product of e to minus lambda p to the I over I factorial e to lambda minus lambda 1 minus p to the lambda to the j over j factorial. It's true for all ij. So that's why, right, in general, x will be Poisson, lambda p, y will be Poisson, lambda 1 minus p, xy independent. Any question? And so with that said, right, what's the answer here? You see here, because x and y are independent, this will be a product of this and that. So the final answer, well, not final answer, but the calculation is just about probable x less than equal to 3. Where x is Poisson 5. So, any question? Okay. So let's look at question 6.17. Let's make this quiz 5. They say 3 points, x1, x2, x3 are selected at random on a line L, what's the probability that x2 lies between x1 and x3? So first of all, right, with this word problem, you have to set up, right, the context. And you kind of have to fill in the blank if something's not given. So what do we need here? Or what should we establish? And what are we calculating? We should establish the joint distribution or the joint behavior, right, between x1, x2, and x3. It's kind of clear that, right, individually they are uniform, right, from 0 to L. But how are they related among each other? Well, I mean, the manner it's described, I don't think there's anything more than independent, right? But in a weird way, right, this is annoying because it should kind of be stated in the problem. But sort of like the only reasonable thing to say here is that they're independent, right? The random variables are independent. And you're asked what probability that x1 is less than x2, less than x3. Right? What's the answer? The answer is 1/3 factorial or 1/6. All right, which sounds as a surprise, right? Or which counts as a surprise, maybe. Because you may have to do a triple integral over this region. But let me tell you, let's say, right, unless we really have to, let's not pull our triple integral. I mean, well, you are supposed to know Calc 3, right, coming into this class. So it's not out of the question that you have to do a triple integral. Well, let's say that if we don't have to, then let's try to find alternatives. And what's the alternative here? The alternative here is exactly the same as what I said at the beginning of the class with the other problem where you know P of x less than y is equal to Py less than x, because they're exchangeable, symmetric. Here's the same thing. Because they're independent and they're identically distributed, so the role of one variable with the other in terms of interaction are the same. In other words, P of x1 less than x2 less than x3 is equal to P of x2 less than x1 less than x3, etc. up to all the permutations, they're all the same. And because there's 6 of them, they add up to 1. Each of them is 1/6. That's it. That's the answer.
Doesn't the wording of the question imply that you can also have the last scenario and it would count as like a solution because x2 is in between x3 and x1?
Oh, you know what? I appreciate that comment. I was not reading the question carefully. I was just focusing on this. So you're absolutely right. The answer is this plus that. No, thank you for pointing that out. Which is 1/3. Yeah. All right, any question? So again, right, you see that independence has so many uses, but just don't assume that independence automatically means simple. Independence in a way is just one quick way to give the joint behavior of random variables. But just because you know that doesn't mean that you can solve the problem very easily. You have to kind of look at how things behave anyway, right? But yes, if you utilize independence, things can work out nicely, but just don't expect that things will work out obviously. Okay, give me a moment. Let me plug in my the charge for my laptop, and we'll continue. All right. So let's move on to section 6.3 if you have no questions. All right. So 6.3, technically speaking, can be 6.2. It talks about sum of independent random variables. Okay. And so let me tell you the theme and the general approach. So first of all, the theme is the following. By the theme, I mean, what's the state of the business? And the state of business is that this is a very popular, and let me just even add, it's a sum of IID random variables. So not only independent, but identically distributed. Okay, it's a very popular thing that you will see. Well, where will you see them? you will see them, for example, in law of large number. Which says that if you take the average of a ID sample, they converge to the population or true average. Easy example, if you toss a coin 1,000 times and you look at the average number of heads, meaning you take number of heads divided by 1,000, everyone would intuitively say that that's the true, right, probability of the coin landing head, which is whatever. But I'm not saying it's false, but what they're quoting behind the scene is the law of large numbers, which behind the scene is the sum of independent random variables, i.e. random variables. You can also have central limit theorem, which we say last time, so I won't repeat. All right. Well, you know what? Let me write it down too. Sum of xi minus mu divided by square root of sigma square n is approximately normal as n goes to infinity. Again, you see, sum of independent random variables, ideal random variables. What else? Let me just say many other things, but one of them would be random walk. You can take any dimensional random walk, but let's say one dimensional, meaning that if you take a model where you go to the right with probability p, go to the left with probability 1 minus p, and if you call x sub n the position where you're at time n after n steps, then it will be just a sum of, let's say, I from 1 to n, where yi are the step random variables. So yi is 1 with probability p, and minus 1 with probability 1 minus p, independent. Right? So these are just some examples. And of course, this is called the sample average. So they appear everywhere in statistics, right? So this is just a common, super common thing you see everywhere. So, but there's no, let me just say there's no standard result, because that cannot be, right? All you say is just something independent, identically distributed random variables, but the result will depend on what the distribution of individual random variables are. So, but that's sort of like a generic approach. But I'm just trying to say that you must study this topic. You must pay attention to this topic if you want to do more work in probability / statistics. On the other hand, they're not easy, okay? I emphasize some independent random variables is not easy business. The textbook appears to make it easy-ish. There's a formula for it, but I'll tell you that I never ever use that formula. But we'll see, okay? So first of all, of course, right? And let's not specialize, but let's say that let's specialize to a simple case where, let's say that you have x and y are independent random variables with densities f sub x, f sub y. The question is to find the density of x plus y. Okay. And let me tell you the textbook's answer. I'm copy, not answer, formula, and I'll copy it down word for word, and I'll explain why it's helpful, but whatever. First of all, of course, we start with at the CDF level. You want to find the probability, right? X plus Y is less than or equal to a number. Okay. And it will be the double integral over the region X plus Y less than or equal to A of the joint distribution, but the joint density is a product because they're independent. And so now you kind of write down this region more carefully. So if you integrate x, x will go from 0 to a minus y, because x less than or equal to, right, a minus y. And y will go from minus infinity to infinity. And it's exactly this formulation that's sort of like iffy when you specialize to distribution, to particular distributions. Because you remember, right, I also wrote something like this before, but I said this is in the abstract because we don't know anything more. If we know more, we have to replace this with concrete limits. And that's the case here, because this looks super nice in the abstract. But when you have this concrete distribution, you have to look careful at the limits. The story is slightly different. But anyway, right, let's continue with the story. So here, this is, sorry, the dx dy. Okay. Y here is a constant, right? So you factor it out. And if you integrate the x, it's just the CDF of the x, right? So it's a CDF of the x evaluated at a minus y. And so that's it. This is the joint CDF of, sorry, not the joint CDF. This is the CDF of x plus y. And what do you know? This, if you take, if you're in engineering, right? And you take a course like 421 or whatever, you recognize this is a convolution of two functions, this and that, right? It's a convolution of two functions. So does calling it a convolution make it any easier? The answer is no. If you ever have to take the convolution of two functions, you'll see that the calculation can be painful. I don't mean painful as in impossible, it's just tedious. Okay, so the notation is something like this. Okay, so it's the convolution of these two functions evaluated at a, because the y is integrated out. But yeah, so let's continue, right? Now, if you want to do the PDF, then you differentiate this with respect to a, right? Okay. Yeah. So this would be the derivative, right, with respect to a of the CDF. Okay. And well, where does a appear? A only appears here. So you can pass the differentiation inside the integral, and differentiating this will give you the PDF. And again, right, a moment of triumph. This is the convolution of the two PDFs. So you can say, and by the way, right, convolution is symmetric. So you can do either a fx convolves fy convolves fx. All right. So that's it. That's the formula, if you will. And I have seen students using this formula to try to solve some problem. I don't want to say that with 100% certainty, but I do recall that they're not so successful using the formula. All right. So fine. If you want to use the formula and you can use it correctly, I have nothing against it. Most of the time, I don't find it that way. So most of the time, I would rework the process. So the value of this is not completely useless here. This process is valuable in terms of the process. It gives you the theme to calculate, yes. But I wouldn't trust so much on the plugging in the answers because of, again, the specific limits you will encounter when you do particular prompts. So let's take a look at the classical problem here, which is so quiz 6. Let's suppose that x and y are independent, uniform 0 to 1. Okay. Meaning what? Meaning that their densities are both 1. And the joint is just a product. Find the density of x plus y. Okay, so that's a question. So let's go through the theme one by one. And I'll tell you some pitfall here. The number one thing I always do when I operate or I have to work on a new random variable is to find the support. Meaning the values the random variable can take. So can anyone tell me what's the support of x plus y in this case? What values can x plus y take? Well, maybe it's obvious, right? But let's just write down from 0 to 2. So, that being said, then it must follow that x plus y is uniform 0 to 2, right? Answer? Nope, definitely not. And probably that's the number one thing student likes to say. Who knows? I'm just saying. So in other words, right, the first thing you want to remember, well, besides the support, is that when you sum individual random variables independently, even whatever, almost always you should not go back to the family you start with. Distribution can and will change. It's really an exception rather than the norm that they stay in the same family. There are only a few cases that they stay in the same family. Okay. Now, case to a point if any one of you who are formula enthusiasts, meaning you love formula, all you want to know is formula, just tell your formula, you can solve the whole problem. Well, here's a formula for you. Can you use that formula to tell me what the answer here is? Oh, let's see, right? Again, oversimplifying a little bit, but let's say that you follow the formula, you say, okay, I see mass infinity, infinity, right? What's f sub y of y? Is 1. What's f sub x of a minus y? Well, it's also 1. So, wait a minute. That's 0 or infinity, whatever.
You should only
So you
integrate
see,
your support.
yeah,
And then you'll have
okay. So what? What should be the case here? Right? Okay, that's correct. But what would be the case here? What would you integrate over? So,
would your support
right?
only be 0 to 1 for dy?
So 0 to 1 then? So
Still
the answer is
doesn't
1.
make much sense, but
Again, you see, it's much more slower than that. But I'm just pointing out that, right? Sure, but no, this is not the right one either. Because if it's 1, then you'll go back to here. And it's not even, if it's 0, 1, 2, you should get 1/2. So the reason is because, right, this guy is only positive between 0 and 1. So you have to work through something like 0 less than a minus y less than 1. So something like y is less than a and y is bigger than 1 minus a, something like that. And then, of course, there's also the restriction that y is between 0 and 1 from the first one. Okay. And let me tell you why. And I think if you work hard enough, you can push this formula through to the right answer. I think, I have no doubt. But that means you have to know what you're doing very, very well. And let me say without boasting that even I don't think I can push through. The reasons I just don't like to push through things I don't understand. Okay. And I'm not saying this formula, I don't understand this formula. I do understand this formula. But as I point out, it's done in the abstract, meaning it doesn't take care of the limit. So when things are simplified down to that level, let's say, then I sort of lose track of what's going on. Let me tell you the true answer here. The true answer here is the density looks like this. And again, it's a very well-known case, so you guys should definitely commit this to your memory. This is the density of the sum of two uniforms. And of course, what's the height here? The height here is 1, right? How do I know? Area of a triangle is 1/2 base times height. So the height should be 1. Okay, good. Total area is 1. Now, why do I want to say that? Well, so first of all, given that this is the result, what would you recognize right away? You would recognize right away that this is a piecewise function. It has two functions, right? One is this and one is that. Meaning that your convolution here has to result in two functions depending on whichever value of A is. You recognize that? Looking at this, I would bet not. You would think that it's only one function out, but we'll have two functions out. Again, I completely recognize that if you work through the support as you pointed out, but in a more sophisticated way, you might recognize there are two possibilities of two range of A's here. But I would argue that for the average person, me included, we would probably fall under the assumption that there's only one answer out, which is wrong, entirely wrong. Okay. There you go. And I think this fact is enough to convince us that we should go back to square one, work out this, and then do things knowing completely the process from beginning to end. Again, right, the point is this process is very useful. I'm just saying, taking the final formula and ignore the whole process, I'm not convinced that it will work for a lot of people. Now, while we're on that topic, right, let's comment on why this is the answer rather than uniform. Right, and this has a lot to do with knowing what the density says. So why would this make sense for the sum of two uniforms? What does this say? What does this, they call it the tent, right? Like a tent shape. What does this say? This says that the sum has the high density over the mid value, which is 1, meaning it's more likely, or it's most likely to be in the middle, and it's very unlikely, let's say, less likely to be at the extremes. Right, the sum can take any values from 0 to 2, but more likely, or the most likely parts in the middle. And by the way, right, this is actually a precursor to central limit theorem, because, right, everyone knows the normal is about a bell shape. And what is a bell shape? A bell shape is something that is most common in the middle and decay out, right, at the extreme. But why would this make sense? And why would that phenomenon happen? Well, these are uniform, right? So really the only thing, so there's no preference over values between 0 and 1. So the only thing that matters here is the number of combinations. You think what? How many ways can you sum up to 2 using numbers from 0 and 1? One way, right? 1 and 1. Same thing with 0, right? How many ways can you sum up to 0? One way. 0 and 0. How many ways can you sum up to 1? Quite a lot. 1/2, 1/2, 1/3, 2/3. 0.48, 0.52, whatever. Do you understand? So there's just a lot of ways to combine to get to the middle, and not too many ways to combine to get to the extreme ends. That's why the distribution will be like high in the middle and decay out at the tail. All right. Now, on to specific calculation, I will do the following. I would start with this standard calculation. Of course, for values of a between 0 and 2, but I have to modify this maybe. And what do I know? Well, nothing besides the joint density. What's the joint density of x and y here? X and y are independent uniform 0 to 1. So jointly, they occupy a square, the unit square. And you can see, right, that is uniform over this unit square. All right. And you can also see then, right, that x plus y less than a is this region. But the moment you draw that, you recognize that there are two possibilities going on. Because the moment you cross the diagonal here, then the region becomes like that. So it's sort of like a different way to express things. Do you understand? So this is a and a, right? So therefore, for 0 less than a less than 1, the probability will be the area, right, of this rectangle, because the total area is 1, which is a square root 2. But for a between 1 and 2, what's the area? Well, the area depends on what you want to pick. You have to know what this is, right? You need to know what this length is. Or how do you know? Well, this is still the line, right? X plus y equals to a. But where this is when y equals to 1, right? So x is equal to 1, a minus 1. Right? So this part right here is a minus 1. Again, keep in mind that a is between 1 and 2 now. So then the remaining part here is the total area is 1, right? Sorry, the total length is 1, right? So the remaining part is 1 minus that, which is 2 minus a, right? And so that's a rectangle, right? So that will be 1 minus 2 minus a squared over 2. Any question? And so you see, I do this purely geometrically by considering the joint density over a square. It's that square right there that's sort of like it's not reflected over this fancy calculation, or not fancy. Take your pick, right? Because of those boundaries that is not reflected over here. And so what's our joint density? Oh, sorry, so what's our density? So the density also comes in two parts. If a is between 0 and 1, then the density will be, differentiate this with respect to a, is a, that function. But if a is between 1 and 2, the density will be differentiating this with respect to a, right, gives you bring down the 2, right? With the minus, bring it out, so 2 minus a. Which is this part. So that's it. That's the density of the sum of 2 uniforms. Any question? All right. So once again, I hope, right, that you take the message as in there's no, who said this? There's no royal road in math or something like that. Well, I'll just take that as meaning that don't expect formulas to do everything for you. Because if that's the case, then we shouldn't be here studying anything, right? Anyone with access to a formula can just do everything. The formula is supposed to capture something in the abstract, in general. But really, the process of deriving the formula is much more useful, because once from the process, you can adapt it to specific scenarios. And by the way, for example, is there any word about geometric consideration in this formula? It says no. And again, yeah, I'm showing you this and it looks simple. But I have had students who took 477, 478, blah, blah, blah. And when I asked them to show me the derivation of the sum of uniforms, they can't. Or they will fumble through the geometry. All I'm saying is that this is not as simple as you think. So after tonight, you wake up tomorrow, you forget all the details. Try to work it out yourself again and see if you remember, right? Or you can rework these things, and you appreciate how subtle a lot of things come together, right? So that's all I'm saying, that the process is important. I can only show you how things work, but you have to really work it out yourself again to kind of master it, right? And not much to say here besides the fact that this is the general formulation. Start with a CDF, work out how it is, and then differentiate it to a PDF. That's all we can say. The specifics change from problem to problem. Okay. Any question? So I figure this is a good place to start. I'll just let you out 2 minutes early. But yeah, so let us continue on Wednesday. Okay.